Welcome back to the channel. We start our lecture number 4 on Quantum Electrodynamics QED. Quantum electrodynamics also reshapes how we understand uncertainty in nature. In classical physics, uncertainty usually comes from imperfect measurements or lack of information. In QED, uncertainty is not merely practical, but fundamental. The theory tells us that even with perfect instruments and complete knowledge of a system's initial state, only probabilities can be predicted. This means that randomness is woven into the fabric of physical law. The path a photon takes or the exact moment an electron emits radiation cannot be predicted with certainty, only with likelihood. This idea forces us to rethink what it means to know something in physics, shifting the emphasis from exact outcomes to statistically reliable patterns. The presence of probabilities in QED does not weaken the theory, instead it strengthens it by matching what experiments actually reveal. When experiments are repeated many times under the same conditions, the results form distributions that agree precisely with theoretical predictions. This consistency shows that probability is not a sign of ignorance, but a feature of the microscopic world. QED teaches us to accept that predictability at small scales takes a different form from predictability at large scales, where averages over many quantum events produce stable and seemingly deterministic behavior. Another important contribution of QED is its treatment of radiation. In classical theory, radiation is a smooth wave emitted continuously by accelerating charges. In QED, radiation is emitted in discrete packets called photons. This explains phenomena that classical theory cannot, such as why atoms emit light only at specific frequencies, and why light can knock electrons out of metals only above a certain energy threshold. These effects reveal that energy exchange between matter and radiation is quantized, and QED provides the rules governing that exchange. QED also helps us understand why certain materials conduct electricity while others do not. Electrical conduction involves electrons moving through a lattice of atoms and interacting with electromagnetic fields. These interactions determine how easily electrons can move and how much energy they lose in the process. While solid-state physics uses its own specialized models, the underlying principles are compatible with QED's description of how charged particles interact with fields. In this way, QED forms part of the foundation for understanding modern electronic materials. The theory further clarifies the nature of light-matter interaction in chemical processes. When a molecule absorbs light, an electron is promoted to a higher energy state. When it emits light, an electron falls back to a lower state. QED explains these transitions in terms of photon exchange and energy conservation. It also explains why molecules absorb and emit only specific frequencies of light depending on their internal structure. This insight connects the abstract theory of quantum fields with the practical science of spectroscopy and chemical analysis. QED also deepens our understanding of polarization, the orientation of light waves. Polarization effects arise from how photons interact with charged particles and how their fields are oriented in space. These effects are crucial in technologies such as polarized sunglasses, optical filters, and communication systems. At a fundamental level, they are manifestations of the quantum properties of the electromagnetic field and its interaction with matter. Another striking aspect of QED is how it accounts for subtle corrections to classical laws. For instance, Coulomb's law describes how electric charges attract or repel each other. But QED predicts small deviations from this law at extremely short distances due to vacuum fluctuations and virtual particles. These deviations are tiny and difficult to measure, but they are real and reflect the underlying quantum nature of the interaction. This shows that classical laws are approximations that emerge from deeper quantum principles. The predictive power of QED also makes it a valuable tool for testing new ideas in physics. If an experiment produces results that differ from QED's predictions, this discrepancy could indicate the presence of unknown particles or forces. In this sense, QED acts as a benchmark theory. Its accuracy allows physicists to identify even the smallest anomalies, and to investigate whether they point toward new phenomena beyond current understanding. The mathematical structure of QED has also influenced fields outside physics, including applied mathematics and computer science. Techniques for handling complex integrals, summing infinite series, and organizing calculations have inspired methods in numerical analysis and algorithm design. This cross-fertilization of ideas illustrates how advances in fundamental science can have unexpected impacts in other disciplines. QED also changes how we think about the concept of interaction strength. The electromagnetic interaction is neither overwhelmingly strong nor negligibly weak. Its moderate strength makes it ideal for detailed study because calculations converge and experiments can be performed with great precision. This fortunate balance has allowed QED to become the most accurately tested theory in science. If the interaction were much stronger, calculations would be harder. If it were much weaker, experiments would be less sensitive. The particular value of the electromagnetic coupling thus plays a key role in making the theory so successful. Another lesson from QED is that complexity can arise from repeated simple processes. A single photon exchange between two electrons produces a basic force. Repeating this exchange many times and allowing for many possible intermediate states produces the rich structure of electromagnetic phenomena. This accumulation of small effects into large-scale behavior is a general feature of physics and helps explain how microscopic laws shape macroscopic reality. QED also contributes to our understanding of time symmetry. The basic equations of the theory work equally well forward and backward in time, even though many physical processes appear irreversible at large scales. This suggests that the arrow of time we experience is not built into the fundamental laws, but emerges from statistical behavior and the conditions of the universe as a whole. QED thus supports the idea that irreversibility is a macroscopic phenomenon arising from microscopic reversibility combined with large numbers of particles. In modern research, QED continues to be refined and applied in new contexts. For example, studies of atoms in extremely strong laser fields explore regimes where traditional approximations break down and fully quantum descriptions are needed. These experiments test QED under extreme conditions and help clarify how the theory behaves when fields are intense and interactions are rapid. Such work not only verifies known predictions but also explores the boundaries of the theory's applicability. QED also informs our understanding of astrophysical processes. In the intense electromagnetic fields near neutron stars and black holes, quantum effects become important in shaping how radiation is emitted and absorbed. Phenomena such as high-energy gamma-ray emission and the behavior of plasma in strong magnetic fields can be analyzed using principles derived from QED. This shows that the theory is relevant not only in laboratories but also in the most extreme environments in the universe. The theory's influence extends to the way physicists think about unification. QED demonstrates that a force can be described by a quantum field and a symmetry principle. This success has encouraged the search for similar descriptions of other forces and for a deeper unification of all interactions. While a complete unification has not yet been achieved, the model provided by QED continues to guide theoretical efforts. On a more conceptual level, QED teaches us that what we observe is shaped by how we interact with the world. Measurements involve exchanges of energy and momentum mediated by photons. There is no observation without interaction. This insight blurs the line between observer and observed and highlights the active role of measurement in defining physical outcomes. It reinforces the idea that knowledge of nature is always mediated by physical processes. The endurance of QED as a theory also reflects its adaptability. It can be expressed in different mathematical languages, interpreted in various conceptual frameworks, and applied to a wide range of problems. This flexibility makes it a powerful and versatile tool. It can describe simple systems like isolated atoms and complex systems like dense plasmas, always using the same underlying principles. In contemplating quantum electrodynamics, we come to see it as more than a technical achievement. It is a way of organizing thought about the physical world, emphasizing interactions, probabilities, and symmetries. It shows that reality at its deepest level may be governed by principles that are elegant yet counterintuitive, precise yet probabilistic. This combination of features makes QED both intellectually challenging and deeply rewarding to study. Through QED, we learn that light and matter are not separate realms but intertwined aspects of a single framework. Photons and electrons are not merely particles moving in space, but expressions of interacting fields. Forces are not mysterious actions at a distance, but the result of exchanges that obey strict rules. Empty space is not empty, but alive with fluctuations. These lessons transform our picture of the universe and invite us to look beyond appearances to the structures that underlie them. As scientific knowledge continues to expand, QED remains a cornerstone upon which further understanding is built. It stands as an example of how far human reasoning can reach when guided by evidence and disciplined by mathematics. It also reminds us that even the most familiar aspects of the world, such as light and electricity, are governed by laws that reveal unexpected depth when examined closely. In this way, quantum electrodynamics continues to shape not only physics but also our broader view of nature and our place within it. Quantum electrodynamics also encourages us to think carefully about what it means for something to be real. In everyday language, we call something real if we can see it or touch it. In QED, many of the most important elements, such as virtual photons and fluctuating fields, cannot be directly observed. Yet their effects are measurable and precise. This forces us to broaden our idea of reality to include things that are known only through their influence on experiments. Reality in this sense becomes something defined not only by direct perception, but by consistent and repeatable consequences. Another important lesson from QED is that nature does not waste structure. The same interaction that explains why electrons bind to nuclei also explains why light bends in glass, why radio waves travel through space, and why X-rays can penetrate matter. There is no separate mechanism for each of these phenomena. Instead, there is one fundamental set of rules governing how charged particles and electromagnetic fields interact. This economy of explanation is one of the most powerful aspects of the theory, and one of the reasons it has endured for so long. QED also highlights the importance of energy exchange in physical processes. Every interaction involves energy being transferred between fields and particles. When light is emitted, energy leaves an atom in the form of a photon. When light is absorbed, energy enters an atom and changes its internal state. These exchanges are not smooth or continuous, but occur in discrete steps. This quantized nature of energy transfer explains why atoms have sharp spectral lines and why chemical reactions involve specific energy changes rather than arbitrary ones. The theory also clarifies why electromagnetic interactions dominate so much of everyday physics. Because electric charge is a common property of matter, and because photons are massless and can travel long distances, the electromagnetic force is both strong and far-reaching compared to gravity at small scales. QED provides the detailed rules for this interaction, showing how it shapes the structure of atoms, molecules, and solids. In this way, it connects the smallest building blocks of matter to the large-scale behavior of materials we use every day. QED further deepens our understanding of noise and fluctuations. Even in the absence of any applied signal, electromagnetic fields exhibit tiny variations due to quantum effects. These fluctuations set fundamental limits on how precisely certain quantities can be measured. For example, they contribute to the noise in sensitive detectors and influence the stability of atomic clocks. By accounting for these effects, QED helps define the ultimate boundaries of precision in measurement technology. Another aspect of QED is its ability to describe interactions over a vast range of distances and energies. The same basic equations apply whether we are studying low-energy atomic transitions or high-energy particle collisions. Only the details of the calculation change. This universality shows that the electromagnetic interaction is governed by principles that do not depend on scale, even though their manifestations may look very different at different levels of observation. The theory also teaches us about the importance of collective behavior. While QED describes individual particles and fields, many observable phenomena arise from the combined effect of enormous numbers of interactions. The reflection of light from a mirror, for instance, is the result of countless photon-electron interactions occurring almost simultaneously. QED provides the microscopic rules for each interaction, while classical optics emerges as an approximate description of their collective outcome. QED has also reshaped how we think about theoretical models. It shows that a successful theory does not have to be simple in every detail, but it must be consistent and predictive. Even though the calculations involved in QED can be extremely complex, the underlying principles are clear and testable. This balance between complexity and clarity is one of the reasons the theory has been so influential. The way QED treats space is also noteworthy. Space is not just a passive stage on which events occur. It is filled with fields that participate actively in physical processes. The electromagnetic field exists everywhere, and its quantum fluctuations affect how particles move and interact. This view of space as an active participant rather than an empty container represents a major shift from classical ideas. In practical research, QED continues to be used as a reference point. New experimental results are often compared with QED predictions to check for consistency. When agreement is found, confidence in the theory is reinforced. When discrepancies appear, they are investigated carefully to determine whether they arise from experimental error, incomplete calculations, or genuinely new physics. This ongoing process keeps the theory alive and relevant. The success of QED also shows how abstract reasoning can lead to concrete outcomes. Ideas about virtual particles and probability amplitudes may seem far removed from everyday experience. yet they lead to predictions that can be tested in laboratories with remarkable accuracy. This demonstrates that human understanding is not limited to what can be directly observed. With the right concepts and methods, we can infer the behavior of systems that operate far beyond the reach of our senses. QED also influences how we think about causation. Instead of a single cause leading directly to a single effect, quantum processes involve many possible intermediate steps, all contributing to the final result. This does not mean that cause and effect disappear, but that they take on a more subtle form. Effects arise from the combination of many potential causes, weighted by their probabilities. This richer notion of causation better reflects the complexity of the microscopic world. Another important theme in QED is the idea of balance. The theory includes processes that increase energy and processes that decrease it, processes that create particles and processes that destroy them. Conservation laws ensure that taken together, these processes maintain overall consistency. This dynamic balance gives rise to stable structures such as atoms and to persistent phenomena such as electromagnetic waves. QED also plays a role in shaping our understanding of scientific explanation itself. It shows that explaining a phenomenon does not always mean reducing it to something more familiar. Often, explanation involves introducing new concepts that are less intuitive but more powerful. Virtual particles, quantized fields, and probability amplitudes are not part of everyday experience, yet they provide a deeper and more unified account of how nature behaves. As experimental techniques improve, QED continues to face new tests. Advances in precision spectroscopy, particle accelerators, and laser technology allow scientists to probe regimes where tiny effects become visible. Each successful test strengthens the theory's standing, while each new challenge pushes physicists to refine their methods and deepen their understanding. In a wider context, QED contributes to our view of the universe as a lawful system governed by consistent principles. Even though individual events are unpredictable, the overall patterns follow precise mathematical rules. This combination of randomness and order is one of the most striking features of the quantum world, and one of the reasons it has fascinated scientists and philosophers alike. The enduring importance of quantum electrodynamics lies in its ability to connect the invisible with the visible, the abstract with the practical. It explains how the smallest interactions give rise to the familiar behavior of light and matter. It shows that beneath the surface of everyday phenomena lies a network of exchanges and probabilities governed by elegant laws. By continuing to study and apply QED, physicists not only refine their understanding of electromagnetism, but also gain insights into how scientific theories are built and tested. The theory stands as an example of how deep questions can be answered through a combination of creative ideas, mathematical structure, and experimental verification. In the end, quantum electrodynamics invites us to see the world as a system of interacting fields rather than isolated objects, as a realm of probabilities rather than certainties, and as a universe in which even empty space plays an active role. These perspectives transform how we think about light, matter, and the forces that bind them together. They remind us that reality is richer and more subtle than it appears, and that understanding it requires both imagination and discipline. Through QED, we glimpse a deeper order underlying the apparent complexity of nature. We see that the interaction between electrons and photons is not just a technical detail, but a window into the structure of physical law itself. And as long as science continues to explore the foundations of reality, quantum electrodynamics will remain a guiding example of how far human knowledge can reach when theory and experiment work hand in hand.